cosine square phi greater than sine square phi, so the probability of AX will increase slightly than probability of AX equal 1. And if sine square phi greater than cosine square phi, then this probability will be slightly greater than this probability. So we try to make the impact of the unknown phi appear in the probabilities of AX equal 0 and AX equal 1. To do this, to achieve these two aims, we will set the parameters as follows. This is our choice, as long as it does the job. So I will set d0 equal mu, d1 equal mu plus 1, and the c's root of the Pauli x gate to this value, such that theta 0 equal this value and theta 1 equal to this value. The first thing we have to understand in this work is that the weak measurement actually is reversible. We can only imagine that if we find AX equals 0, then as we expect that psi 0, the probability of psi 0 will increase. And if we find AX equal 1, then the probability of psi 1 will increase. The more we find AX equals 0, then psi 0 will increase gradually. Actually, this is not going to happen. This section will show that if we found, after arbitrary number of measurements on AX, if the number of times we found AX equals 0 equals to the number of times we find AX equal 1, then the probability of the system will be restored to the initial state. As if finding AX equals 0 cancel finding AX equal 1 and vice versa. They cancel each other. Every time we find AX equals 0, cancel the effect of finding AX equal 1. To show the reversibility of the weak measurement, we have to show this lemma to prove this lemma. This lemma shows that what we are trying to prove here, that this formula is equal to 1. Actually, we are just trying to show that according to our choice of theta 1 and theta 2, that cosine theta 1 equals sine theta 0 and sine theta 1 equal cosine theta 0. So directly this formula holds. Using this lemma in the probability of psi 0 and the probability of psi 1, and any time in the run of the algorithm, if J0 equals J1 in this formula, then we will see that the probability of psi 0 equal to the initial probability. So we didn't change anything in the system at any point that J0 equal to J1. This is a reversibility. We are not going to lose anything in the algorithm. The second thing we have to consider that this is a probabilistic operation. When we apply measurement on AX, we don't know if we are going to find AX equals 0 or AX equal 1. This is a probabilistic operation. What we want to do is that if probability of AX is 0 greater than probability of AX 1, then we found AX equals 0, but this is not always the case. We can still find probability, we can still find AX equal to 0. So the counter of J0 may increase in the wrong direction. Maybe probability of AX0 will be greater than probability of X1, but still the counter for AX equal 1 or J1 will increase faster. Actually, this will not happen because the algorithm will maintain stability condition for some time. If we have two events, one with high probability and one with low probability, it is not likely that every time we apply measurement we get the low probability. So we have a chance, I'm going to show this in a minute, we have a chance that the algorithm, even if the algorithm moves in the wrong direction, it still has a chance to restore the correct movement. Due to the reversibility of the weak measurement, we don't care now about J0 and J1. We don't care about the counters, but we care about the difference. How many times J1 is greater than J0? Because they cancel each other. So we rewrite the four master equations as follows with delta J, not J0 and J1. What we're going to use these four master equations, I will assume that the stability condition holds for the algorithm as long as probability of AX0 greater than half. Actually, all the mathematics shown here can be done assuming that probability of AX1 greater than half. This is symmetry. You have symmetry here in the paper. So if we just use the master equations here in the stability condition, we will find that delta J equal to this value. Means that probability of AX0 will still greater than half, will satisfy this condition for some time, giving the algorithm the ability to restore moving in the correct direction if it starts moving in the wrong direction. So it means that the algorithm will maintain the stability condition even if the random walk, the probabilistic measurement, goes in the wrong direction for at most. During this number of steps, we still have high probability that the algorithm restore moving in the correct direction. Actually, we can now even control the strength of the weak measurement. The strength of the weak measurement we are going to define as the distance that the random walk has to move from the initial state to the state that are epsilon far from the projected state. Using the projective measurement, the strength is equal to 1. After one measurement, we are going to reach to the projected state. But now we have distance, we have number of measurements we can do until we reach to the projected state. This strength actually can be controlled as we are going to see. Now, I'd like to know how many iterations I am going to apply on this state until it reaches to the projected state, or at least epsilon close from the projected state. After doing the calculations, we find that actually we can do mu square iterations until the quantum state reach to the projected state. So if we increase mu, if we increase the dummy qubits in the system, we will make this, we can make this as weak as we want, or as strong as we can change the strength of the weak measurement as we are going to see now. But we don't want to reach to the projected state. So we decide to stop early. We decide to stop at iteration J less than J projected. The probability of reading the correct solution is shown here, and the random walk, this is a random walk. We can here we can see that if we use a small number of dummy qubits, then the random walk will move fast. This is 0 probability, 1 probability. As long as we increase the number of qubits, the change, the disturbance on the system will be very weak. So we can control the speed of the random walk using the number of qubits. This is the probability of success of the algorithm. We start with a random guess, and as more as we run the algorithm, the probability of success